Father, thank you for the opportunity to be here and to study matter, the things that you created by the power of your word, the things that you uphold with your hand. Just pray that you would help us, help me to teach well and to be clear and to teach in such a way that it gets through to everybody. And I pray that you be with each student here and help us to ask questions when we don't understand, and to pay good attention, have good insight in the things that we're studying, to have good recall on. For your glory, we pray this in Jesus' name. Amen. Well, let's start with a little bit of just review. So, atom. What about the structure of an atom real quick?
It includes protons, neutrons.
Protons, neutrons, electrons. Where will I find these parts? Somebody other than Matthew. What's going to be in the nucleus? Protons and neutrons. And where will I find these electrons? These shells that are orbiting, right? And they go around the nucleus because the nucleus has what charge? Positive, and the electrons have negative, and like charges attract. Why don't they just crash in?
Because they're moving.
There's such velocity, right? Very good. And how many electrons fit in the first shell?
2.
2. And the next one? 4.
8.
8. Okay. And there, we start to get into some rules past that we're not ready for right now. So we're just going to deal like the first. Good. We're just going to deal. We're going to deal with just the first 10 for right now, first 10 elements or so. So, how many do they want to see in that second shell? How many electrons do they want to have? They want to have 8, 2 in the first. They want to have 8 in the second, right? What if they don't have 8? Then what are they going to do?
They're going to react with something to gain the rest or lose the rest.
Yeah, they may try to gain some electrons, they may try to lose some electrons. If you're something like lithium and you have 3 total electrons, 2 in the first, 1 in the second, are you going to find somebody to give you 7 electrons?
No.
No, that's not realistic, right? So what's your best option?
Lose.
Just give that one away, and lithium does that. I mean, if you took a piece of lithium and stuck it in water, you're going to have fire, you're going to have smoke, you're going to have light, you're going to have all this stuff, because it's going to be just handing out electrons like crazy, okay? If I had something like fluorine that has 9 total electrons, 2 in the first, 7 in the second, and it desperately wants another electron, it's going to try to steal one from somebody, right? By the way, when I transfer an electron from one to the other, what kind of bond is that?
Ionic.
Ionic. Okay. The other options are to share electrons, right? To try to fill these.
Covalent.
And so I will form a what? What's that called when we share electrons? Or when we give them away or take? What is this called? The activity of electrons between 2 atoms.
Bonds.
It's called a chemical bond, right? We have 3 types of chemical bonds. What are they?
Ionic.
Ionic.
Covalent.
Well, ionic and then 2 flavors of covalent. Ionic.
Metallic.
Nope. Ionic. Polar. Non-polar. Okay. We got to have these. By the way, this is a great segue. There are 3 quizzes up. Quizzes, like, that's just what they call them. Think of them as homework assignments, think of them as practice, think of them as like 10% of your grade, think of them as however you want. They are open. I would get on there and I would take them. And I would take them until I got 100% on them. They're not terribly overwhelming. One's like 11 questions, one's 8 questions, and the other I don't remember how many it has, but it's not crazy. I need to take this real quick. I'm sorry. I'll be right back. Yes, ma'am? Oh, of course, of course. Yes, it is. No problem. All right, thank you. Sorry about that. Protection is very important. Okay. So go on and do that. those quizzes are going to show you what you need to know for a test, okay? And it'll show you what you do know and what you don't know. It'll give you practice. It'll give you practice in what we're going to do right now also. So atoms are made up of protons, neutrons, electrons, right? So I'm going to do two atoms, and I want you to tell me, are these ions? Are they isotopes? Are they different atoms? Are they neutral atoms? What are they? Okay? So the first one is this. What's the relationship between atom number 1 up here with 4 protons, 6 neutrons, 2 electrons, and atom 2 down here with 4 protons, 6 neutrons, and 4 electrons?
The bottom one is neutral, the top one is charged, and they're both the same atom and the same isotope.
Good. Slow down. When we look at the protons, these have the same number or different number?
Same.
Same number, right? So they've got to be the same or different elements?
Same.
The same. Atomic number 4, do you have your periodic table of elements? If you do, get it out. If you don't, let me know and I will hand you one. Need one? Okay. Okay. So which element is atomic number 4? It's beryllium. Okay. So both of these are beryllium. They have the same number of neutrons. What if they had different numbers of neutrons? What would that tell me?
They're different isotopes.
They're different isotopes. If I have the same atomic number, but a different atomic mass, that means that they're isotopes. So far, they're identical, but then I get here. One of them has 2 electrons, one has 4 electrons. Is there any charge on this atom?
No.
No, right? But is there a charge on this atom?
Positive one.
There is. It's a positive 2, right? And so this is an ion, okay? So I would identify these or this as an ion. Let's try another one like this, okay? Let's do, do not just answer, just wait. Make sure. 17 everywhere, yes. And literally 17 everywhere, right? What's atomic number 17? What atom is that? Or what element is that?
Chlorine.
It's chlorine, okay? So these are both chlorine. Are these ions?
No.
They're not, right? An ion is going to have a charge. It's going to have a difference between the protons and the electrons. These are the same. Are these isotopes?
No.
No, they both have the exact same number of neutrons. So these are identical, right? In every which way. Let's do one more. By the way, you have one of the homework is just practice like this, okay? You've got to be able to just recognize these pretty quickly. Last one we're going to do right now. This would be the first thing I would look at probably.
Protons.
The number of protons, the atomic number. What is, what's the one on top? What's number 18 there?
Argon.
Argon. And what's number 17?
Chlorine.
Chlorine. So right away, I already know the answer to this, right? What are these?
Different elements.
Different elements. Okay. You can do this. You're on a good path. All right. Why don't you real quick take a look at argon on your periodic table? Okay. So once you go down, what's right below argon?
Krypton.
What's right above argon?
Neon.
Neon. Okay. What's the atomic number of neon?
10.
10. How many electrons should it have? 10.
10.
If I have 10 protons, I'm going to have 10 electrons, right? Okay. How many will it have in its first?
2,
2. How many will it have in its second?
8.
8. Does it want to make any bonds whatsoever?
No.
Okay, good. That's going to come back in just a little bit. Molecular formulas and structural formulas. So, molecular formulas. Here's your book's definition of a molecular formula, okay? It says a molecular formula is a representation of a molecule that uses chemical symbols to indicate the types of atoms followed by subscripts to show the number of atoms of each type in the molecule. Let's do, should have had some examples written down, shouldn't I? Yeah, let's do CH3, no, CHF3. CHF3. Or we could write this, could I write this another way? It would be better to write HCF3. Let's do that. I want you to draw this. Or I'd love for you to tell me what this is. Let's do CF. This would be an easier one to do. What's the C?
Carbon.
Carbon. This tells me I have how many carbons?
1.
1 carbon. And what's this?
Fluorine.
This is 1 carbon and 4 fluorines, right? How does it spell fluorine on yours? Is it F-L-U-O-R? Or is it F-L?
Actually, it's very hard to read, so I think.
Okay. I believe it's F-L-U-O-R. Go right there. Okay. So I have 1 carbon, I have 4 fluorines, right? I can draw this. That's going to be what we call a structural formula. Let's go ahead and draw this. Can you do it for me? It's tough. So I need a pen. Do you need a pen? I got pens.
Yes.
Not a clue. That's fair. That's fair. Take a look at where carbon's at. Take a look at where fluorine's at. Oh, okay. My little boy. Oh, goodness. I rigged a slip and slide for my kids. Y'all know what a slip and slide is? Yes, I rigged one of those. I went to Harbor Freight and I got a big old tarp, folded it in half, laid it out, took the hose, put a spray nozzle, put a stake in the ground, zip tied that joker to it, and it was falling. So then I took the lawnmower, put it behind, and lapped it, so it was good. So day 1, huge, great job on the slip and slide. They had a blast. Day 2, it had come down. So my 6-year-old boy is out there, and my wife said he's tried 12 different ways to fix this thing. He just wouldn't give up. That's just life, man. Who cares if you get it wrong? Eventually, you know? So, this is really important. Carbon has how many total electrons?
6.
Has 6. How many in the first?
2.
2. How many in the second?
4.
4. Okay, so let me just draw carbon, okay? I'm gonna draw carbon like this. This is what we call a Lewis dot structure, okay? In a Lewis dot structure, we only show the valence electrons, okay? I don't have to worry about the first two. I don't have to draw E's everywhere, all this craziness. I'm just gonna draw a C with 4 dots, okay? Super easy. Fluorine. Fluorine is atomic number what? 9. How many electrons in the first? 2. How many in the second? 7. So fluorine would look like this. It's gonna, and by the way, when you do, here's a little hint. We're a little ahead of ourselves with this, but that's okay. This is something you got to know, and soon enough. You start and you go, oh, these markers. I say this every time, don't I? You start in one spot and then you just go around the clock, okay? Until I use them all up. Now, know that I can just pivot this, so I'm going to just erase one of these and put it here, okay? So there's fluorine with its 7, right? How many does it want?
8.
It wants 1 more. It wants to get to 8, so it wants 1 more. You all said the same thing 2 different ways. So what is it going to do?
It's going to take 1 from carbon.
It's going to bond. Now, I could bond it with fluorine. Fluorine gas is a thing, but this is 1 molecule, right? Not a whole bunch of craziness. So best thing to do is just connect the dots. So far, so good?
Yep.
All right, so do that. And then we'll come over here and we'll go, all right, there's another fluorine. Let me go here. 1, 2, 3, 4, 5, 6, 7, right? In fact, I'm going to do this a bunch of times. You'll do the same thing, okay? I'll do yours. Feeling good?
I had it right.
I already had it. It's okay.
Do another one of these in practice. Look at the difference between a chemical formula and a structural formula. It contains similar information, but one's 3-dimensional, right? And the other one is just numerical, essentially. It's give me information. But I have to do a whole lot of thinking to figure out how this starts to look like this. Okay? All right. So with this, not too hard. This is just going to be connecting some dots, right? Okay. We feel pretty good about that? Okay, good. Let's do another one. Please do NH3. Now, hydrogen's not going to be too tough, right? Hydrogen is atomic number 1. How many protons does it have?
2.
Hydrogen is atomic number 1. How many protons does it have?
1.
1. How many electrons does it have? 1. So you know it's just got 1 in the valence shell. That's easy. Nitrogen, look up where it's at, figure out how many electrons are in the first, how many are in the second, and then draw it, okay? Oh my goodness. When you draw nitrogen, or when you think about nitrogen, how many protons does it have?
7.
It has 7. 7 protons. If it has 7 protons, how many electrons does it have? 7. How many in the first? 2. How many in the second? 5. So when I go to draw this thing, it looks like this. Right? That's what the Lewis dot structure for nitrogen looks like. Did you get something pretty close to this?
Yes.
Okay, well that's all right. Here's the important question, everybody. If you got something different, do you see the difference in how you get here? Okay? It's not where you're at, it's where we're going. Do we know how to get here? And now, being here, can you figure out what NH3 looks like?
Question.
Yeah.
Has hydrogen just got no dots?
No, hydrogen has one dot because it has one electron.
But wouldn't that be in the first ring though? So don't you only do the second ring?
We're doing the valence ring. So by definition, valence is simply the outermost.
Okay.
And since it only has a first ring, its valence just says, oh yeah, that's a great question. So I just play connect the dots. And by the way, this is ammonia. Stuff in the bottle that stinks.
Which reacts with bleach.
Yeah, don't do that. I was doing a lab one time, testing pH on chemicals, and my student aide poured all the, when it was done, they were doing me a favor and cleaning everything up, and happened to pour the bleach and the ammonia down the same pipe. Now, my next class came in, and all of a sudden the kids were like, Mr. Douglas. And I go, what? And they're like, I don't know, it just doesn't smell right. I'm like, y'all are crazy. And then I get up and I go over there and I see fumes coming up, and I go, oh, I know what just happened. Clear the room. So we taught out in the hall for about half an hour, turned on fans. So this is ammonia. Let's do another one. Let's do, what do we want to do? Well, let's just do this. Keep it very simple, very classic for the moment, okay? Just good old water. How many protons does oxygen have? 8. How many electrons? 8. How many in the first? 2. How many in the valence? 6. So how many dots does it get? 6. So let me draw an O and put 6 dots. Remember to work in 90 degrees around this thing. That will help you. Right? So there's my oxygen. Yours looks something like that.
Yes.
And you're really getting it. So this is good. So now let me come and put an H, right? That's what water looks like. Okay? Well, very good. Let me give you one more challenge. This isn't any big deal at all whatsoever, but it's good practice. I want you to draw just the Lewis dot structure for lithium, or let's do it for carbon, let's do it for neon, let's do it for sodium. Oh, let's throw in boron. You need boron. Let's do boron. Okay. Do the electron dot structure. Do the Lewis dot structures for those. Okay. It's the first thing I want to look at.
Atomic number.
Atomic number. It tells me the number of protons. From that, I know how many electrons. Then I know how many go in the first shell.
2.
2, and the rest will go in the valence until the valence is full. One of these is actually going to break the rule. I said it goes past atomic number 10, but it's only to number 11, so you'll be okay. How many go in the second shell?
8.
8, so anything past that is going to bump out to the next one, right? All right.
How many go in the third shell?
You don't need to know that right now.
Okay.
That's where we start getting into some rules and things.
Okay, done.
Actually, even on that one, still, it's 8. We start to get into,
I guess 10.
we will very shortly. From
No.
just like Hawkeyes.
No, I just went there for, like 2 years.
You live there.
Yeah,
Gotcha.
I lived in Texas for
All right. How are we feeling?
Good.
Yeah, it's just that one that I'm kind of like,
Okay. How many, well, and you're right that that's wrong, so erase that. Follow your rules. How many go in the first?
2,
How many go in the second?
8.
8. So if I have 9 to go in the second, that doesn't work, right?
Yeah.
So what do I need to do? I can't put 9. So where does the 9th one go? Kicks up to the next level. We go to a third shell.
So
And how many will have it?
2, 1, just the one.
Just the one. Got it. Lithium, how many protons? Say 2. 3. Sorry, say 3. Lithium has how many protons? Say 3.
I was like, what?
3. How many electrons?
3.
3. How many in the first?
2.
How many in the valence?
One.
1. Good. Carbon, how many protons? 6. Electrons.
6.
How many in the first?
2.
How many in the valence?
4.
4. Neon, how many protons?
10.
10. How many electrons? 10. How many in the first?
2.
How many in the valence?
8.
8. Sodium, how many protons?
11.
11. How many electrons? 11. How many in the first?
2.
2. How many in the second? 8. What do I do with that last electron? Bump it up to the third level. Sodium has 1. Boron.
5.
Sorry, let me pause there. Make sure everybody make sure you're good on sodium. Make sure you know why sodium looks like that. Ask questions right now.
Would that be the equation for every single time with every other, like, element?
So we'll get to, later on, we'll talk about hybridization. And it's going to get a little weird. For right now, this is going to work almost every time, okay? Certainly for everything smaller, argon and actually for everything calcium and smaller, this will always work, okay? All right. Boron, how many total electrons?
5.
5. How many in the first? 2. How many in the second?
3.
3. Good. Let's do one more. I'm going to throw one at you here. Let's do aluminum. Do aluminum. Al. Atomic number, what, 13? Is that right?
Yes.
Good. If it's atomic number 13, how many protons? 13. How many electrons? 13. I can do this math, right? How many in the first? 2. How many in the second? 8. 2 plus 8 is? 10. That leaves me 13 minus 10 is? 3. How many in its valence shell? 3. It would look like this.
It looks exactly like boron.
Y'all feel good about this? So far so good?
Yes.
Okay. All right. How many bonds will lithium make?
1.
Not 7? No, it can't make 7 bonds. It doesn't have 7 electrons. It can make exactly 1 bond, right? How many will carbon make? 4. How many will neon make?
9. None.
Good question. 8 or none? Which is it?
None.
None.
None. It has 8. He doesn't want to make any. You couldn't get him. Good luck. Sodium, how many bonds?
1.
1. Boron, how many bonds?
3.
3. All right, and aluminum?
3.
3. Good. That's great. So everybody feel good right now? Okay. Awesome. So we got here, which I didn't expect to, but we got here, which is good. It's good. We need all this, and I feel like you probably understand things better because we were talking about chemical formulas and structural formulas. So a chemical formula tells me how many. Right? So if I have CH4, it tells me how many, what type and how many of each element, right? 1 carbon, 4 hydrogens, right?
Isn't that methane?
It is methane. If I have, oh my goodness, sometimes my brain just does not work. If I have NH3, let's go back to that. It tells me what? One nitrogen, 3 hydrogens. Now, one thing that's also good about this, in this, the way this is written, it does tell me what's bonded to what. I know that these hydrogens are bonded to this carbon. I know that these hydrogens are bonded to this nitrogen, right? I could have something like this. What's the hydrogen bonded to?
Carbon.
The carbon. What's the nitrogen bonded to? The
Carbon.
carbon. And hydrogen and nitrogen do not bond together, right? Does that make sense?
Yes.
You want to try this one? What atom should I begin with?
C.
Let's begin with carbon, because everything's bonded to carbon, okay? So draw your carbon. Carbon has 6 protons. How many electrons? 6. How many in the first? 2. How many in the second? 4. Okay?
Oh, I just realized.
Now, let's do hydrogen next, because that's easy, okay? So hydrogen, let's put it over here. How many electrons? 1. So I'm going to put it. How many bonds is it going to make? 1. Super easy. Okay. Now I'm going to come over here, I'm going to put my nitrogen. How many total protons? 7. How many electrons? 7. How many in the first?
2,
How many in the second?
5.
5, right? Now, I'm going to tell you this. If you put your double electrons here, it's going to mess you up. You just have to know that this thing it can rotate in space however you need it to. So wherever you need to put those electrons, you put those electrons. If you put them here, you're going to look at this and you go, I don't know what to do. If you put them here, you're going to end up going, I don't know what to do. If you put them here, you're going to end up going, I don't know what to do. But if you happen to write it just right and it looks like this, then I think it becomes very clear what to do, doesn't it? You just connect the dots, and you go here, and you go here, and you go here. Fair enough? Yeah? We like this? Good, let's do one more. Draw that. Where do I want to start?
Carbon.
Crawley with carbon. Run my nitrogen like this. I think this is a big enough hint for how to draw this, right? Just totally good on this, Louis? Good. So what kind of bond do I have between my carbon and my nitrogen?
A double bond.
Double bond. It's going to need to bond twice. Nitrogen over here is going to get another hydrogen, right? I know that because this hydrogen is over here on my chemical formula, right? So far so good. So I know there's a hydrogen bonded to that nitrogen. I know there's 2 hydrogens bonded to this carbon. The only question I have left is how many bonds to make between hydrogen and carbon, and they each happen to need 2, so that becomes easy. Right? So there's a lot of information in that molecular formula. All right, excuse me.
What molecule is that?
I knew you were going to ask me that. I know that's cyanic acid or hydrogen cyanide. That I don't know what that's called. Douglas Special. All right. Well, I want us to watch a video on 2 videos actually on the periodic table. Okay, one is on its discovery, which will help us to understand why it's so distinctly useful and important. And the second one is on just how to use it, like There's so much information on that that will make your life easy if you know what's going on with it. It's arranged, there's a reason that it's arranged the way it is. I mean, look at that thing, it's weird, right? It's like a strange castle. Why is it arranged that way? Why am I telling you that's so useful? Well, we're gonna discover that right now, okay? So, let's go here. We go to our Moodle. Oh, look, there's a quiz. Let's see if I can get. Okay. Let's go. Okay, here we go. That's not the one. Let's go to your class. So just to show you, in case you have not been doing anything with Moodle, right? You should have already done all this stuff. What is this? Let me go to your view. This is what yours looks like, right? You should have posted to the forum. Go ahead and just do that. It's not any big deal at all whatsoever. Just go ahead and do it. Notes from chapter 1, especially all that vocabulary stuff. Lesson 2 video. They're not all up here. Remember, at least twice. I think I had trouble with the video. I've got that figured out now. The rest of these are all making it up there. You had some practice stuff to be able to do on your own. And then, you know, all the things that I've been showing you in class. And then there's these quizzes: atomic structure quiz, polar ionic, nonpolar quiz, isotope, stuff like that. We're gonna, if any of these videos, anything I show you or do, I'm gonna put here, okay? So you can click on this. And here we go.
The United Nations declared 2019 to be the International Year of the Periodic Table, celebrating the 150th anniversary of the discovery of the periodic law. Early in 1869, Russian chemist Dmitry Mendeleev was in a predicament that many people are familiar with. He was facing a deadline. He had delivered the first volume of his inorganic chemistry textbook to his publisher, but was struggling with how to organize the second volume. The struggle would culminate in a remarkable discovery, a system that classified all of the chemical elements. In March 1869, Mendeleev delivered a full paper to the Russian Chemical Society, spelling out the most significant aspect of his system: that characteristics of the elements recur at a periodic interval as a function of their atomic weight. This was the first iteration of the periodic law. Mendeleev was far from the first chemist to attempt to organize the elements by atomic weight, or to recognize that characteristics recurred on some sort of regular basis. Through much of the 19th century, chemists had worked to find an organizing principle that encompassed all of the known elements and that could be considered a law of nature. Mendeleev's system was not perfect, but it had the hallmarks of a scientific law, one that would hold true through new discoveries and against all challenges. One of the unique aspects of Mendeleev's table were the gaps he left. In these places, he not only predicted there were as yet undiscovered elements, but he predicted their atomic weights and their characteristics. The discovery of new elements in the 1870s that fulfilled several of his predictions brought increased interest to the periodic system, and it became not only an object of study, but a tool for research. In the 1890s, William Ramsay discovered an entirely new and unpredicted set of elements, the noble gases. After uncovering the first two, argon and helium, he quickly discovered three more elements after using the periodic system to predict their atomic weights. The noble gases had unusual characteristics. They were largely inert and resistant to combining with other substances. but the entire set fit easily into the system. The discovery of radioactivity in 1896 seemed poised to destroy the periodic system. Chemists had always considered elements to be substances that could not break down into smaller parts. How could radioactive elements, which decayed into other substances, be considered elements? And if they were, how could so many fit into the very few gaps left in the table? Chemists and physicists working together began to understand the structure of the atom, and were soon able to explain how the periodic system worked on an atomic level. Rather than atomic weight, atomic number, that is the number of protons in the nucleus of an atom, determined the characteristics of an element. Rather miraculously, organizing the elements by their atomic number rather than their atomic weight did not change the arrangement of the periodic table. In fact, understanding how electrons fill the shells orbiting a nucleus explains some of the anomalies that have plagued the periodic system from the start. The periodic table, the visual representation of the periodic law, is recognized as one of the great achievements of chemistry and as a uniting scientific concept relevant to the physical and life sciences alike. But the periodic table is also an important aspect of science education. Mendeleev and many of the others who developed systems to organize the elements did so in their roles as chemical educators rather than as chemical researchers. He was writing a textbook for his students at St. Petersburg University when he developed his periodic law. At the time, the only available chemistry textbooks in Russian were translations. Perhaps most important, he continued to draw revised versions of the periodic table throughout his life. Neither Mendeleev's first attempt at the periodic system, nor his most popular table from 1870, look much like the periodic table that hangs today on the wall of most chemistry classrooms, or appears inside the cover of most chemistry textbooks. Now, there are probably 1,000 different periodic tables of the elements. The majority of these tables look fantastical in comparison with the castle-like table that is found in classrooms. Curved forms such as spirals, helices, and three-dimensional figures of 8 were wildly popular amongst educators well into the 20th century. These were generally deemed to be easier for students to use to learn about the elements and the relationships between them than a flat, two-dimensional table. The thing about a flat, two-dimensional table, however, is that it fits easily onto one page or as a poster hanging on the wall. It doesn't require special fold-outs or printing techniques. It can easily be shrunk or expanded to fit as needed within the text. And there were plenty of tables to be found amongst all the curves. So why this one table? Where did it come from? There were so many similar tables that in some ways it just evolved over time. But chemists frequently point to the table created by Horace G. Deming, a professor at the University of Nebraska, as the progenitor. Deming's table first appeared in his 1923 textbook, General Chemistry, and was slightly modified in each edition until the final one appeared in 1952. Chemical educators lauded Deming's table, but scientific supply companies made it famous. Merck handed it out as part of a promotional campaign in the 1920s. The Welch Scientific Company sold it in the form of wall charts and in standard page-sized and best pocket editions. Eventually, it was included in standard reference handbooks, such as the CRC Handbook of Chemistry and Physics and Lang's Handbook of Chemistry. By the 1950s, versions of Deming's table could be found in the majority of chemistry textbooks. Today, renderings of the table can be found on almost any type of consumer good: shower curtains, coffee mugs, keychains, phone covers, and the list goes on. The story of the periodic table is in many ways one about textbooks, things that are usually given short shrift. Consider that Mendeleev made his name in the Russian chemical community by writing a textbook, his inorganic chemistry textbook won a prize, and then became famous by discovering the law while in the process of writing another textbook. And the periodic table we see in textbooks and in classrooms got its start in a textbook. If nothing else, The story of the periodic law should make you rethink your opinions of textbooks and textbook authors. And maybe too, remember the creativity and innovation that can occur in the face of a deadline.
All right. So who discovered the periodic table? Or the periodic law?
Mendeleev?
Mendeleev, Russian guy, right? And they didn't know all of the elements at that time. That was one of the incredible things. When he put his table together, it had holes in it. And he's just going, I see patterns that are happening. And that is because I believe these patterns, I believe there's something here, and I think there's a hole here, I think there's a hole here, I think there's a hole here. And later on, they discovered those elements, and they fit. They had, relatively speaking, the right atomic mass. They definitely had the right atomic number. They had the right reactivity. They had the right properties. They fit this idea of recurring trends or periodic trends and properties in the elements. And we'll talk more about that coming up. First, I'm going to show you this next video. I think.
If you can find it.
If I can find. Should be good. Let's go back here.
Also, I found out what that chemical is.
Okay.
It's a medication called hydrazine.
There we go. I would not have known to call it that. All right. So the first one was kind of background information. I think it has some cool stuff, definitely worth knowing, definitely in the book. This is like, okay, you need to know this stuff, okay?
Hi, it's Mr. Anderson, and today I'm going to take you on a tour of the periodic table. A book that I've been reading, and I'm not quite done, but it's really fascinating, is called The Disappearing Spoon. It's written by this guy over here. His name is Sam Keen. If you want more information, you can go to samkeen.com. It's neat. It's got a lot of trivia on the periodic table. But it's essentially about the history of the periodic table. In other words, it's not the science, which I'm going to talk about today. It's more about the people who discovered the elements. It goes all the way from the Manhattan Project to Mr. Bunsen, the inventor of the Bunsen burner, and Mr. Lewis, famous for Lewis dot diagram. So it's a fascinating read. And it's getting at the history behind this, which is the periodic table. Periodic table, we're going to come back to this in just a second, and we'll review some of the things from this podcast. The thing you may be puzzled about is what's up with the name of the title, The Disappearing Spoon. Disappearing Spoon is actually written about this element. It's called gallium. It's a poor metal. And the neat thing about gallium is that it has a really low melting point. And so if you mix your tea with a spoon made of gallium, so let's take a look at this video over here on the side. The minute it goes in the tea, you can see that it starts to turn into a liquid and then kind of melt away. Thus, the disappearing spoon. The problem with this, I was, like you are saying, well, let me Google it. Let me buy one of these spoons. It seems cool. It's also highly radioactive, and so it may not only be a disappearing spoon, but it may be a disappearing hand if you deal with gallium too much. So let's get to the periodic table. So here's our periodic table. Periodic table, first of all, the vertical columns are going to be called groups, and so this would be 1 and 2.
Let me do this real quick. If you do not have your periodic table, you need one. Anybody not have one on them right now? Anybody else has one? Okay, good. I'm sure I've got one.
And it goes all the way over here to number 18, which is on the side. And the periods are going to go down the side. So this would be 1, 2, 3, 4, 5, 6, 7. And so we're going to see these periodic properties. In other words, as we go and look period to period to period to period, you'll find that there are similar characteristics. Let's go through it then. And I'm going to try to use different colors and highlight each of the different areas. So let's start with the first one. First one are going to be these metals. These metals are called the alkali metals, and it goes all the way from lithium at the top to cesium at the bottom. So these.
Oz. Why did he not circle hydrogen?
It doesn't. It's not a metal.
It's a guess.
It's a gas, okay, thank you. It's a gas, it's not a metal, right? So the rest of those are metals. you might just like circle the column from lithium down to francium. But you're right, this is not very clear, is it?
No.
I will do better for you in the future. I'll figure that out. But those are, what do you call this? Alkali. Let me spell that for you, okay? Feel free to mark up all over this thing. I will give you another clean one later, okay? Alkali metals.
Called alkali metals.
Oh, these
Alkali metals all have one valence electron. That means that they're highly reactive. And so this picture down here,
So, on your periodic table, let me just draw a very, very poor man's sketch of this thing, okay? You got this, right? And then you drop down one, and you got this, and then I've got like 10 things here in the middle. And then I come up a wee bit here, and I go over. I go in 1, 2, 3, 4, 5, so I'm gonna go 1, 2, 3, 4, 5, and then this last one's gonna come on up again, right? That's not bad. Kind of looks something like that. Yes? Okay. How many protons does hydrogen have?
One.
How many electrons?
One.
How many valence electrons?
One.
How many valence electrons does lithium have?
One.
How many does the next one have?
One.
Next one?
One.
Next one? Next one? Next one? How many bonds do these things want to make?
One.
One. If I'm looking for an element and I want to know how many bonds it makes, all I have to do is look at this. If it's in that first column, it only makes one bond. So I can write above that, I'll just write hydrogen, okay? Because I know that hydrogen wants to, and I'll do it this way. Hydrogen has one valence electron, okay? That's useful, isn't it?
Yeah.
Like at that point, you don't have to think, you just have to look. Let's do the next one. Over. Beryllium. How many is beryllium going to have?
Two.
2. Right? So I can do Be. I know it's got 2 electrons. We're going to ignore the middle for a minute. He's going to talk about it, and we'll do some stuff with it in a second.
All of them
But let's
have two valence electrons.
Let's go over to boron, okay? Boron is atomic number 5. 5 electrons, how many in the first? 2, how many in the second? 3. So I go like this. How many bonds do you want to make? 3. Carbon,
6.
how many in the second?
4.
4, how many bonds?
4.
4. Then next up is nitrogen, right? Nitrogen's going to have 5, and it's going to want to make 3 bonds. And then oxygen's going to have 6, and it's going to want to make 2 bonds. Then fluorine is going to have 7, it's going to want to make 1 bond. And I'm going to skip helium for a second. There's a reason helium's up here, by the way. Okay? Okay, I can do helium. I'll do helium right here. Helium has 2. And then down here I have neon, right? I'm going to do neon to the side. Neon has 8. Why is helium above neon? Why is it helium over here above beryllium?
Because it only has 2 electrons.
It has 2 valence electrons, but its valence shell can only hold 2 electrons. So it's full. It's what we call a noble gas or an inert gas. It will not bond. And so it put it with all of the other, I'm sure throughout history there have been charts that have had helium either in some weird spot or maybe here, but helium does not act like beryllium does. Beryllium is pretty reactive, whereas helium does not react at all. So I need to put it with the other elements that don't react at all. Well, they're all over here. what's the link? Why don't they react at all? Because their valence shell is full, and that's true for helium, and for neon, for argon, and for all the rest of them after that. So that's why helium's over here, okay? Excuse me. Here we go.
Got lithium, sodium, all the way through cesium. If you want to have fun on YouTube, just look at alkali metals and you'll see people thrown into water and you get these huge explosions. And that's because of their valence electrons. Next to them are called the alkaline earth metals. So let me advance our picture. So these are the alkaline earth metals. It goes all the way at the top with beryllium, all the way down to the bottom at radium. So this is alkaline.
So with alkali and alkaline.
These all have 2 valence electrons, and so they're reactive as well. They tend to form oxides with oxygen, magnesium, calcium. All of these are important in living things, and they tend to be fairly stable. In other words, we can find them on our planet in a raw form. Next up, we've got the halogens. Halogens are going to be over here on this side. So this would be a halogen right here: fluorine, chlorine, bromine, iodine, astatine. These all have 7 valence electrons, so that means they would love to get one more electron, so they're not super stable. Chlorine, pictured here in this block, is in a liquid form. It normally occurs as a gaseous form. It's a nasty gas. It was used as a poison during World War I. And these are the halogens right here, highly reactive. Right next to them, however, are the most unreactive of the elements that we have, and these are going to be called the noble gases. So helium, neon, argon, krypton, xenon, and radon. All of these have 8 valence electrons, and these are going to be called the noble gases. Really stable. They've got complete outer energy levels or valence shells, and so they're really, really happy. Unlike their halogen neighbors, which are right next to them. Okay, cool thing about them, if you look down here at this picture, you put any of the noble gases in a tube, run electricity through it, they're going to fluoresce as electrons kind of move to higher energy levels and then fall back down. So if you look at neon lights or lasers, are all made up of these noble gases. And if you ever have heard of inert gases are gases that don't react with anything. We use those in like MIG welding, be an application of that. Okay. Next are the schnapps. Schnapps are a way that I like to remember the non-metals. And so I'm going to circle these. So here's carbon. Then I'm going to go way over here and circle hydrogen. And then we're going to do nitrogen and oxygen and phosphorus and sulfur and selenium. So these are all called the non-metals. The reason I wrote down schnapps is that these are all things that are vital inside living material. So carbon is what we're made up of, nitrogen makes our amino acids, oxygen is used to get energy out of our food, we use phosphorus in our DNA, sulfur in our proteins, and even selenium, which is not part of schnapps. We need micro amounts of that. It's been linked to deficiencies in selenium can actually, perhaps, cause cancer. Okay, next one then are going to be the transition metals. And so if we were to circle those on here, transition metals are going to be all these down here.
Okay. He said some things there about these. First of all, they are non-metals.
So there are only 3 columns that you did that.
Did I do too many things?
Yes, you did the column with fluorine.
Chlorine, nitrogen, oxygen, fluorine. What did I do wrong?
He didn't do the fluorine column.
Oh my goodness, thank you. He's like, what is going on? I knew something was off. Thank you for catching that. That's helpful. Okay. It's hard when you freestyle and stuff. Okay, so these are these are all gases. These are all gases. Or I should say these are non-metals. Non-metals, 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 right? Everything else is metal, or what's called a metalloid, which we'll talk about in just a moment. It's its own special category. But these have a name, right? Noble gases. These have a name, halogens. He called all the rest of these schnapps. I never heard that before in my life, but you can remember it, so it's kind of useful. I'm gonna just write it here, okay? CHNOPS, was that it?
No,
What did I miss?
there's no H.
No H?
I don't think.
There should be, because he's got hydrogen.
Oh, wait, never mind.
All right, so carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, right?
Yeah.
Carbon, hydrogen, nitrogen, oxygen, phosphorus, what's my last one? Is it selenium? So 2 S's, right? So here, I'll put it like
No,
that.
I think you didn't put another S.
I know, I'm putting like an S.
Wait, so it is included in the schmuck?
What is?
So,
Yeah, he's got it. So let's look at what he's got. You can see it up here. C for carbon, H for hydrogen, N for nitrogen, O for oxygen, P for phosphorus, S for sulfur, and another S for selenium. Okay? Between your noble gases, your halogens, and these chenops, everything else is a metal. Everything else. Or a metalloid. We're going to cover that, like I said, in just a second. Okay? Feel good right now? Okay. Here we go.
Perhaps. No, it's cancer. Okay. Next one then are going to be transition metals. And so if you circle those on here, transition metals are going to be all these down here. These are the transition metals. Transition metals have weird numbers of electrons. In other words, the ones that they're showing outside are variable, and so they all look the same, but they all have different characteristics. And so these are called the transition metals. Example would be gold, and so gold is going to be right here as a transition metal, and here's a block. This is the largest block ever of gold. I think it's 250 kilograms, so like 600-pound bar of gold. Neat things again, that verticality, silver is right above that, copper is right above that. They have similar valence electrons, and so these are all going to be similar. Next group then on the periodic table is going to be the poor metals. And so if we go to where those poor metals are, poor metals, let me find a good color. Poor metals are going to be, let's go right here, and here. Here. These are going to be the poor metals in here, and so metals are going to be over in this group. This is gallium right here. This is the picture of gallium that was that disappearing spoon, remember, that melted away right at the beginning. These are going to be somewhat good conductors, but not as good as the true metals that we find over here in the transition metals. Next group then are going to be the metalloids, and so a good color might be red if I could find that. There we go. So the metalloids are going to be here. So that's boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. These are all going to be the metalloids. And these are all semiconductors, and what that means is that they conduct electricity, but they don't fully conduct electricity. I've got a block of one of them. This is actually a log or a large amount of silicon, and so this is a silicon crystal. What they do is they grow it into these great cylinders, and then they slice it off, and then they can stand silicon chips out of it. So it feels a little bit lighter than it would if this is just a true metal like iron, for example. And if we run electricity through it, we can kind of control the amount of electricity through that because it's a metalloid or a semiconductor.
Okay. So we've got transition metals. That's, you'll understand more about those later in the class. For this point in time, we will not work with any of these. This is where stuff gets weird with your electrons, okay? We come over here and we've got two groups that we haven't talked about yet. He did for a second. One is metalloids. Notice how I drew it. How did I draw it? At an angle, because the metalloids go in an angle. Boron, silicon, germanium, arsenic, selenium, tellurium, polonium, right? So they notice they're on this slant. They're in between the metals and the non-metals. They have characteristics of the metals, they have characteristics of the non-metals. They're kind of in a world in between. He was talking about how metals are great conductors of electricity. You don't believe me? Just unfold the paper clip and go find yourself an outlet. Okay? But something like silicon is not the best. It does a decent job, but not the best. And electricity does not just flow right through it, which is very useful. That's a characteristic of the metalloids, right? So some characteristics of the metals, some characteristics of the non-metals, and you see that very clearly in this arrangement of the elements. You might not see that in another arrangement. Okay? So far, so good? All right. Let's see what we got. We're almost done with this.
And then the last thing I put on here was uranium. There's a general trend that as we go farther and farther and farther down the periodic table, our size is going to get larger and larger and larger. So when we get down to things like uranium, these are actually uranium cubes that were used in the Manhattan Project. Atoms are going to get larger and larger and larger. So when we go down to the bottom, this is uranium. Most uranium is in the form of uranium-238. That means it has 92 protons and tons of neutrons. And so the farther we go down the periodic table, things tend to get radioactive. In other words, parts of them tend to decay or to fall apart. One other interesting part here, this is the lanthanides and the actinides. The way a periodic table really should be organized is that...
Pause there. There's a brick of atoms or elements there at the bottom, right? It's detached. So he gave you the lanthanides and the actinides. So I'm going to just kind of draw that here. Okay? I know there's 10 of them. 10 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's 2 bricks. So we've got lanthanide. And what's how do you spell it? Yeah, how do you spell it?
These 2 rows here at the bottom.
I'm just going to write ACT.
ACT.
Okay, so lanthanides and actinides. Okay. So this is weird, right? Why are these here and not there? Well, because, and I think he's going to talk about this in a second, if I were to put it all on one, you would need a whole other sheet of paper. What we'd actually have to do is this. You have to do something like this. Should make it just crazy big. And since these rarely get worked with, it's a lot easier to just take this out and smoosh it together. Okay.
Should actually be inserted here. And the reason that most periodic tables don't show it that way is it would make our periodic table incredibly long, and so it really wouldn't display well
It's not
on poster.
Maybe this book.
Yeah, it's 14.
I knew that.
I just remembered because I did a chemistry class once,
Mhm.
and we did the, like 1s2,
Oh, yeah.
that thing.
When you get to your,
And then when you get to this,
Yeah.
it gets to 14.
okay. That's good. Well, all right, guys. That's enough for today. We're just a few minutes short of when the class is scheduled to end. I don't want to start a whole new subject. Really, I will get also a periodic table quiz up. Please go take those. Look at me. Grade-wise, I am happy. There's a reason I've left them open. They don't have time limits. There's a reason you can take them as many times as you want. I want you to have any grade you want to get out, okay? I want you to learn the material. That's my goal. That's the reason I took the time, okay? If you're not doing them, you're putting yourself at a huge disadvantage. Please take the time, go look at them, go do them. If you haven't read your book, go read your book. It's going to say the same stuff I'm saying in a different voice. And that's really, really useful. Okay? Y'all got any questions for me? All right. God bless you. Have a great day.
So funny, I was drawing those dot structures differently. This is how I was taught.
That's true too. Here's the only problem with this. This works for people who know.
Yeah.
But when you're first starting out and you've never done a Lewis dot, you don't need to do every dot. And then once you're experienced with it, then you do it. You do it like this.
Yeah.
Yep.
Oh, good.
Hey, thank you.
But yeah,